much. So indeed, I mean, I'm here to communicate this weekend, and don't hesitate to come up and talk to me. It may not seem like there has been that much to Johnny. To me, it seems like there's been a fair amount, but I enjoy it. A nice way that maybe the graduate students and faculty members, other people might want to collaborate here that we were talking about in the elevator is we should come up with a Wikipedia article for the finite element exterior calculus. So maybe if that's the kind of thing you like to do, you might think about that. Okay, so far we've only talked about the continuous level. We've defined this abstract notion of a Hilbert complex, which is motivated by, in which a key example is the Durham complex, which we've thought is concretely of spaces of functions and vector fields and so forth on Rn and girls and divs and so forth. I mentioned that you can, of course, do that also in n dimensions, sort of defining all those operators at once as with different exterior calculus, and we'll get to that. But now I want to return to the question. So we said that if you had one of these Hilbert complexes, then you get a sequence of PDEs out of it called abstract Hodge-Laplacians, one at each level. And you can formulate that either as strong form PDEs or as a weak form primal or a mixed formulation. And they're all equivalent to each other. And then that's where we are now. And then the question is, well, we're going to be moving towards when we're going to want to solve those by finite elements. We're in an abstract framework now, so now we're going to solve them by subspaces that later will be the finite elements. So really the two biggest things I have to do are, one, in this abstract setting, say, well, if we had a sequence of subspaces and we applied our variational formulation with those subspaces, we get some sort of approximate solution. Is that any good? And then the other thing is then we want to go to the concrete applications like Durham, and in a more sophisticated sense like elasticity that Rick talked about yesterday and so forth, and say how can we actually construct subspaces. That actual construction of subspaces is a big piece of finite element exterior calculus we won't touch until, I guess, tomorrow. But today we'll talk still in the Hilbert complex framework of approximation. So here's a point I've already made enough times, I barely have to repeat, that we have a primal formulation and a mixed formulation, but the primal formulation is a problem. There are cases in which it works, but there are cases where it gives real difficulties, and so we're interested in the mixed formulation. So this is exactly what's been on previous slides. We're given an F and WK, and we want to find a sigma and a U in VK minus 1 and VK. In other words, they're in WK minus 1 and WK, but they're in the domain of D. And if there are harmonic forms, we want to find a harmonic form P. And then we have that first equation, which basically, well, not basically, which actually says sigma is equal to D star U. And then the second equation, which represents that D of D star U plus D star DU is equal to F modulo harmonic forms. And the last one makes U unique if there are harmonic forms. Notice there's a big difference between the primal formulation and the weak formulation, which is that the primal formulation, which is du dv plus d star u d star v equals fv, is completely symmetric in d and d star. But this one, there is no d stars. D star is handled weakly here or implicitly, and d is handled explicitly. The way you do d is you just apply d. So that's the nature of the mixed method. And now the Galerkin method is the obvious thing. In each of the spaces Vj, you choose a finite dimensional subspace Vjh. Once you do well, skip the next two lines and let's drop down. I probably should have put that first. Once you have your finite dimensional subspaces, oh, I see why I did it. Okay, let's take it in order again. Take your finite dimensional subspaces Vjh, then we can talk about the cycle Zijh. That would just be the null space of D, but D restricted to the subspace. So things in the subspace for which D is 0. And then Bjh would just be the range of D restricted to the preceding subspace. So Bjh is D of Vj minus 1h. And then you could ask for things in Zijh which are orthogonal to Bjh. And that would be sort of a discrete harmonic function. So the definition, you don't pick HJH. It's determined by the other choices as the things in ZJH orthogonal to BJH. And I want you to notice that ZJH is a subspace of the true Z. These are things in the null space that are also in the subspace. And BJH is a subspace of the true space of boundaries. These are boundaries of things. These are Ds of things that happen to also be in the subspace. HJH is not contained in the true H, because the true H would require orthogonality to all of B, not just to the subspace. Okay, now we have these spaces, and we use two of them, VK minus 1H and VKH, and the harmonic forms at the K level, and we do the Galerkin method in the completely obvious way. We have to find a sigma H in VK minus 1H, and a UH in VKH, and a PH in HKH that satisfy the exact same equations as the true mixed formulation, but with the test functions restricted to those spaces. Okay? Another way to think about it is that this is a discrete saddle point operator over these spaces, and we look for a saddle point. In many cases, there are no harmonic forms, so HH is 0. And if also HKH is 0, then those terms are out, and this is just a standard conforming, this is what is called a conforming Galerkin method, because the subspaces VK minus 1H and VKH are contained in the VJs, in the true VK minus 1 and VK. If there are harmonic forms, then this is really what's called a non-conforming method, not in a very substantial way, but these terms are non-conforming because HKH is not a true subspace of HK, right? So in general, we don't expect that HKH is contained in HH, so there's a nonconformity there. What does nonconformity mean? It means that the exact solution, U, can't be expected to be satisfy this equation. It's not orthogonal to discrete harmonic forms. It's orthogonal to true harmonic forms. So we'll have to deal with that when we prove our estimates. One thing we don't have to worry about is whether there exists a unique solution to this problem. There's always a unique solution to that problem, no matter how you choose the subspaces. And let's prove that. You just take the obvious choice of subspaces, of test functions. You take tau is equal to sigma, and H and V is equal to UH, and you plug in there. And I'm assuming F is 0, and I want to show that sigma H and UH and PH are 0. So I get sigma H squared. Then I'm going to add the two equations, so the UH d sigma H and the d sigma H UH will cancel. And then I'll get plus DUH squared plus PH UH is equal to 0, if F is 0. Now I can take Q is equal to PH, and then use the last equation, and then this term is gone. So whatever we choose as subspaces, we get sigma H is equal to 0, and DUH is equal to 0. So that means UH is a discrete cycle. And then we look at then we look at the first equation again, and we see UH d tau equals 0 for all tau in VH. So this says that UH is orthogonal to the discrete boundaries. It's orthogonal to everything in D. We know sigma H is 0, so we only have that term left. So UH is a cycle that's orthogonal to boundaries, so that says that UH is a discrete harmonic function. And then we take the last equation, which says UH is orthogonal to the discrete harmonic function, so UH is 0. So now we have sigma h is 0 and UH is 0, and then the middle equation tells us pH is 0. Okay, so you can pick any spaces you want. You can do the Galerkin method. But absolutely key observation that anybody who's worked in mixed methods would be aware of is that although you can choose various spaces, they're not going to work in the sense of having a stable approximation that gives you good accuracy of the solution. So we'll see shortly that we need to make hypotheses on these spaces in order to have any sort of decent convergence theory. Okay, any questions? Yeah, Si Chang. You don't. You define it. It's certainly a finite dimensional space. It's a subspace of ZH, and ZH is a subspace of VH. We will see that if our hypotheses are met, the dimension of HJH is equal to the dimension of the true harmonics. So if you have two holes, you'll have a two-dimensional space. But you need to calculate that space. Okay? So you might ask me, how do you do that calculation? How do you do? I'm not going to say it right now, but basically you solve an eigenvalue problem. You have a big finite element matrix, and you know it has a two-dimensional kernel. You compute the kernel. Okay, so these are the assumptions. So this is probably the most important take-home message of finite element exterior calculus, at least the abstract part, is that if you want to solve the mixed Hodge Laplacian, the subspaces you choose have to satisfy three properties. The first one is the same for all Galerkin methods for all problems. They have to have decent approximation, because otherwise you can't approximate with them. So you can formulate this in many ways. An absolute minimum requirement is that for anything in the true solution space, the best approximation by something in the finite element space and the finite dimensional space goes to 0 with some parameter h. So I don't really have a parameter h, but let's imagine we have a family of subspaces parameterized by h. We need to have approximation. Of course, this is not good enough to get convergence estimates. For that, you would assume that for W in some smaller subspace of the solutions, this is order h to the r or something like that. So that's completely standard, and that will happen because we'll use piecewise polynomials of some degree r. But there are two key properties in addition to the approximation property. And the first is the subcomplex property, which just says that the D of the k minus 1 space is contained in the k space, and the D in the k space is contained in the k plus 1 space, so that we have a subcomplex here. Now, you notice in the mixed method, we only use two spaces. On the other hand, we have a D operator that maps the second space into some other space, so we really need three spaces. That's all we really need. So although I'll sort of state these properties like we have the whole complex, you can always put zeros at the dots and only look at this little piece of the complex if you want. Okay, and here is the key assumption. Bounded cochain projections. So we now have a complex, or a little piece of a complex, vk minus 1, vk plus 1. And we have a subcomplex, because we assume that the subspaces we choose form a subcomplex. And now we need to assume, for the abstract theory, that there exists a projection operator from the full space down to the subspace. And that should be a projection, so leave the subspace invariant. It should be bounded uniformly in H. In other words, the bound on this thing will enter the constants in the error estimates. And it should commute with D, a cochain map. D pi is pi d, so a bounded cochain projection. In this context, boundedness could mean two things. It could mean pi hv is less than, in the V norm, is less than V in the V norm. Or it could mean pi hv in the W norm is less than V in the W norm. The W one is a little bit harder to achieve, because if we had that property, pi hv in the W norm is less than a constant times V in the W norm, then we would have d pi hv in the W norm would be, well, that would be equal to, because we have a cochain map, pi h dv in the W norm, which would, because pi h is bounded in the W norm, would be less than a constant times dV in the W norm, which is less than V in the V norm. And if we put these two together, we get pi hv in the V norm is less than a constant times V in the V norm. So this implies this. In practice, we can always achieve the harder one. But for the time being, we only need the weaker one. Pi hv is less than V. So I'm going to assume for the time being V boundedness. Later I'll need W boundedness. No, I went from the W norm to the V norm, which is by definition includes D. Dimitri? D on the discrete space is the restriction of the D on the top space. It has to be exactly the same. Okay, so that's why we were talking about a conforming finite element method on those terms. Right, the same operator on the discrete level is the true. There is a paper by Ari Stern and Michael Hulst that weakens that a little bit, basically because they have a surface and an approximate surface, and they use the D from the approximate surface on the subspaces. Okay, so now I think you'll agree with this by the time we're finished today. Those two basic assumptions, subcomplex property and bounded cochain projections, just lead to many, many conclusions. Everything sort of follows neatly from those. And so that's what I'm going to be doing for the next couple of slides. So let's start drawing conclusions from these things. So the first thing that's very nice is, since we assume the subcomplex property, this is a Hilbert complex. Well, what's a Hilbert complex? It means I need Hilbert spaces W and closed operators, defined on densely defined operators with closed range, because I want a closed Hilbert complex. So first of all, I have to tell you what the W's are. Well, WH is just VH, but with the W norm. On the finite dimensional level, well, it's dense, so the two spaces must be equal. You can't be dense in a larger dimensional space. So this is really the domain complex and the whole complex are the same thing. And the D operator, of course, is the discrete D. So D is D restricted to VH. VH. And these are, of course, Hilbert spaces. And this is, well, all operators on finite dimensional Hilbert spaces are bounded operators, so it's a bounded everywhere defined operator. So it's a very simple example of a Hilbert complex, a finite dimensional Hilbert complex. Okay, but since it's a Hilbert complex, everything we studied about Hilbert complexes applies to it. It has an adjoint. It has its own harmonic forms, which we already defined. It has a Hodge decomposition. It has a Poincare constant. It has an abstract Hodge Laplacian. The abstract Hodge Laplacian has a unique solution. It's all for free, because we're sticking in the Hilbert case context. So let's use some of these things. There's an adjoint operator on this Hilbert complex that maps some domain in here to domain in here. It's densely defined. These are finite dimensional, so actually the domain V star KH is the same space yet again. So we also have this is equal to V star KH. And we have D star H, which goes from that space to the next space, in the previous space. And it's defined just by this relationship that D star H UV, or U tau, is equal to U D of tau for all tau in the subspace. You have to be very careful here. D star H is not equal to D star restricted to the subspace. Because D restricted to D star, the true D star, would have to require orthogonality against everything here in the domain of D, not just in the subspace. In fact, there's an open question that appeared originally in the topology literature, whether d star h is a consistent approximation of d star. I can make that, I'd have to look it up and get it clear, but it's a very precise statement, which we tried to prove, Ragnar and I, for a while, and didn't succeed. So that's something people could think about. So you, two cases of the Laplace. One is zero forms. In that case, it's zero because the operator goes back, so you mean the other case. And actually, d star h was invented by Ravi-Artoma in their original paper. So the Ravi-Artoma method is sigma tau minus u div tau is equal to 0, and div sigma v equals fv. That's the mixed form of the Laplacian. And Ravi-Artoma said, define grad A. So then they did this with subspaces here. And then they used tau and piecewise constants here, right? And they looked for a sigma h in the Ravi-Artoma space. And the UH and piecewise constants, right? And so they said, define a grad H operator from the space of piecewise constants to the space of Ravi-Artoma vector fields by grad H of U, L2 inner product with a Ravi-Artoma vector field tau is the same as U minus the divergence of tau for all tau in RT. So of course you can determine something in RT by telling you it's inner product with everything else in RT. That's the adjoint of the discrete divergence operator. So in this case, d, h, is div restricted to the Ravi-Artomas, and d star h is grad h. Now that's, of course, a global operator. So it's a way to find a gradient of any piecewise constant, which is some sort of global thing, which roughly is, represents the gradient. I think even in this case it's not known to be consistent, but I need to remind myself about this story here. Just to get put in a little historical. So as we'll see, these Ravi-Artoma elements actually were invented by Whitney, and in topology, not in finite elements, and they tried to analyze them to prove convergence of eigenvalues of the Hodge-Laplacian, Dojuk and Patodi, International Congress of Mathematicians in the 70s. And they tried to do it using the primal form with d star h, and they had a hell of a time because it's not consistent. Okay, what else do we get from having a discrete, having a Hodge Hilbert complex at the discrete level? Well, we get an adjoint and we get a Hodge decomposition. So of course, B star h is defined to be the range of d star h. Everything is defined in the same way because it is just an example of a Hilbert complex. So d star h of vk minus 1h is b star h. And we know for all Hilbert complexes, the base space breaks up as the boundaries plus the harmonic forms plus the range of b star. And we also know this, we have the discrete Hodge decomposition, and we have the discrete Poincare inequality, which is the first one that's quantitative. The discrete Poincare inequality has that the norm in V of any cycle, of anything that's orthogonal to the cycles is bounded by the norm of dz. So if you mod out the null space of D, then this inequality holds with some constant. Now this is the only one that's quantitative, and we're going to want to have control over that constant because that constant determines the well-posedness of the problem and the stability. So we're going to want to prove somehow that this is independent of H. But at the moment that's not implied or said here because we're just using the fact that for each H we have a Hilbert complex here. So a key thing will be bounding that Poincare constant. Okay, so now I said that when you have this Hilbert complex structure, you get a lot of things. And here's one theorem, which is a pretty powerful theorem that comes directly from these assumptions. So suppose we have a closed Hilbert complex at the continuous level, so a closed Hilbert complex. We choose some finite dimensional spaces, they form a subcomplex, and there exists a V-bounded cochain projection pi h. I need a tiny bit of approximation. I need to know on the finite dimensional space of harmonic functions that that they're not orthogonal to our subspace, that there is something in the subspace that's a better approximation than 0. Okay, so it's almost unimaginable that you could ever come up with a subspace where this wouldn't be true, but I do need it. Under those assumptions, then pi h, well, pi h is a cochain map, so it induces a map from the cohomology of the top complex to the cohomology of the discrete complex. And the cohomology is canonically isomorphic to the harmonic forms. So pi h induces an isomorphic from the harmonic forms to the discrete harmonic forms. And that map is an isomorphism. So that's why the discrete harmonic forms always have the right dimension. Moreover, not only they have the right dimension, but they're close to the true harmonic forms in the sense that the gap between these two finite dimensional spaces is as good as the approximation of harmonic forms. So you take a harmonic form, normalize it so it has norm 1, and ask how good is the pi h approximation of it. Actually, it's time to make a observation. I thought I did make it on the previous. Oh, I did make it on the previous page, but I didn't say it. The pi h operators, besides being commuting, cochain maps, are bounded and projections. And any map that's a bounded projection is quasi-optimal approximation, right? Because if I take u minus pi h u, because pi h is a projection, that's the same thing as saying u minus v minus pi h u minus v for all v in the subspace, because v equals pi h v, because pi h is a projection. And pi h is bounded, so this is less than 1 plus the bound on pi h times u minus v. So pi h always gives the best approximation up to a constant, which is the bound of the operator. Yeah. Let me see. Can I remove the 1? Do I need some assumptions on this? For any projection in, okay, might be that I can get rid of the 1. Zikatanov and Shu. But I can't give such an easy proof. It is a beautiful result. Okay, so this gap in between the two spaces is no more than the approximation of something, the approximation error, and typically we would know that this is order h to the r, so that would be no problem. What's the gap between spaces? So this is a general notion when you have two Hilbert spaces or Banach spaces, and you have two subspaces, even infinite dimensional subspaces, you can have a gap, and this gap has the property that if the spaces are orthogonal to each other, it's equal to 1. If the spaces coincide with each other, it's equal to 0, and the smaller it is, the closer they are. It's roughly the angle between the spaces, cosine, a sine of it, or something like that. And how do you do it? Well, you take a harmonic function, normalize it to be norm 1, and say how small is the best approximation in the other subspace of that harmonic function. And then you do the same with the two things reversed, and the maximum of those two is called the gap. Okay, but so this is a very important theorem that says as long as you have the subcomplex property in bounded cochain projections, you match the homology. And why is it so important? Well, we know that the condition that U is orthogonal to the harmonic forms, that's a part of the problem that we're trying to solve. And we know that we can only solve the problem modulo the harmonic forms. If these didn't have the same dimensions, the discrete problem would have the wrong number of conditions. Suppose there are no discrete harmonic forms, but there are true harmonic forms. Then you can't impose your condition that U is orthogonal to harmonic forms on the discrete level. That's what went wrong in the annulus example I gave on the first day. Okay, so let me give this proof. Do I dare to give it without my notes, Sandy? Let me get them at least close so I don't get too nervous. But let's just try to do it. So what I want to do is I want to show that pi h induces an isomorphism from the true harmonic forms to the discrete harmonic forms. So this really is the same as it induces an isomorphic from the true homology group, cohomology group, to the discrete cohomology group. And these are, of course, defined to be Z mod B and ZH mod BH. Okay, one aspect of it is easy, that it's a surjection. So we have to show it's a surjection and an injection. And actually, the surjection we showed on the first day, any cochain projection is a surjection. And remember what the argument was. A projection means that if you first do the inclusion and then the projection, you get the identity. So therefore, the induced map of the induced from the inclusion followed by induced from the projection is the identity. So the induced map from the projection has to be onto. So this one is easy. Okay, so now we need to show that we need to show that if the equivalence class in Z mod B is taken by pi to 0, then the equivalence class was already 0. Right? That's what it means to show it's an injection. If it takes something to 0, that thing was already 0. So we take a Z in the cycle space, and what's the map that pi induces on Z? This is, you take pi Z, and that's a cycle in ZH, and you take its equivalence class in ZH mod BH, and we're assuming that's 0. So we take a Z in Z with the property that pi HZ is 0 in Z mod BH, ZH mod BH, so that means pi HZ is in BH. And what we have to prove is that Z is in BH, in B. We have to prove the original Z is B, so the original equivalence class is 0. Okay, everybody with me? So all I'm doing is using the definition of cohomology classes as equivalence classes in Z mod B and Z mod BH. And the fact that the induced map is just the cohomology class of Z goes to the cohomology class of pi Z. Okay, so how do we do this? We use the Hodge decomposition. So Z has, like anything, 3 pieces. Z is equal to some part that's in B plus some part that's harmonic plus some part that's in B star. But Z is in the null space of Z, so it's only these two parts. These are where the cycles lie. This is not a cycle, so that one's gone. So the Hodge decomposition shows us the null space consists of the boundaries plus the harmonic forms. Okay, now we look at pi Z. So that's pi ZB plus pi ZH. And our assumption is this belongs to BH, that pi Z belongs to BH. We're trying to show that this ZH vanishes so that Z is actually in B, that the harmonic part of Z is actually 0. Okay, so now let's see, pi HZ, this is in ZH, and that's contained, so let's see, what's going to be my argument here? This thing is in ZH, this is in BH, and the whole thing is in BH. BH is contained in ZH. So every term in here is in BH except for this one, and since they add up, this has to be in BH. So we conclude from this that pi h of the harmonic part of Z is in BH. And now, how are we going to conclude that ZH is equal to 0? I need to get some more orthogonality. Got a quick hint? You don't remember either. Okay. So that's, I told you. What? Good idea. Pi h of ZH is equal to D of some rho. Some rho h in VH. So this is in B. You have the next step? It's really slick and easy. I just don't remember. Okay, so we look at ZH, which in these notes is called Q. And so ZH is orthogonal to B because it's harmonic. And, okay, of course, that's what we have to do. And that's it. So ZH is orthogonal to B because ZH is harmonic. That's the other kind of H, that's the harmonic H. Right? We took Z and wrote it as a B and a harmonic H. And harmonic H, by definition, is orthogonal to B. Okay. Now, pi H ZH is, so I don't need this step, actually. Thanks. But pi H ZH is in BH. And BH, of course, is part of B. So ZH is orthogonal to its projection. Well, actually, so now we're done. Remember what I said is our approximation property was minimal possible. At least the harmonic form shouldn't be orthogonal to everything in the space. But let's just follow it through carefully here. We have ZH is equal to pi h of ZH plus ZH minus pi h of ZH. And these two guys, and then we move this over, this guy is orthogonal to this guy. So then we use the Pythagorean theorem and we get that ZH minus pi h ZH squared is equal to ZH squared plus pi H ZH squared. Because the two things are orthogonal to each other. But we assume that this thing was strictly less than ZH, and here it shows it's greater than or equal to ZH. So that's a contradiction. Okay, so basically what I'm using at the end is if something was orthogonal to its projection, then projecting it to the subspace doesn't make it any better. But I'm assuming a minimal approximation property. That's where that property comes in. Okay, so that rather simple argument shows that the induced map on homology is also an injection and therefore an isomorphism. And I don't know, it's sort of, should I do the gap stuff now, or it's a sort of similar proof. Yeah, well, so let me give you some idea of the gap. Actually, if I have my notes in front of me, it's 4 lines. So why don't I do that? The gap comes down to 2 error estimates, one for approximation of something in the real harmonics and one for something in discrete harmonics. So the first one is the best approximation in the discrete harmonic space of a harmonic function is good as the approximation of that space by the pi h of that function by the pi h operator. Okay, so that's the first estimate that will be used to prove the gap estimate. So what does this say? It says take a harmonic function, approximate it by a discrete harmonic function, then that's as good as you get by approximating by anything in the subspace using the pi h operator. So it says the discrete harmonic functions are near the harmonic functions, because this is a quantity that's easy to bound, where this is going to be order h to the r. Pi h is a good approximation. This wasn't obvious because we didn't know whether the discrete harmonic functions were near the true harmonic functions. This says they are. So let's prove that. So we take a harmonic function, and so then that has 3 pieces. Well, okay, then if I just project it as the discrete harmonic functions, I claim that's the same as projecting it into the discrete cycles. It's probably good to have our Hodge decomposition up here, that VH is equal to BH plus HH plus ZH perp, and this is ZH. And Q, being harmonic, Q is orthogonal to B. That's part of the definition of harmonic. And B contains BH, so Q is certainly orthogonal to BH. So its projection into ZH has a BH part, which is 0, because it projects to 0 in BH. So the projection into ZH and the projection into HH are the same. That's this inequality here. For an arbitrary function, P into ZH would be P into HH plus P into BH. But for a harmonic function, the P into BH part is 0. Okay, now pi h of Q is in ZH because Q is in Z. That's the other part of being a harmonic function, that you're in Z. And so therefore pi h of Q, being a cochain map, is in ZH. So this should already imply this. This says that the best approximation of Q by a discrete harmonic function is the same as the best approximation by something in ZH, and so that's better than any other approximation in ZH, and pi HQ is another approximation in ZH. That's all there is to it. Now the second estimate. What should be obvious? Which is a projection? This is the orthogonal projection, the best approximation. But this is into the space HH, and this is into a much bigger space VH. Yeah, but no, that's not true. No, that's okay. That is a point of confusion, so it's good you brought it up. So what do we have? We have V and VH, and that's where pi h goes. Then we have the homology classes H. I'm not putting K's here, so I won't put K's here. And HH. This is the cohomology, which is by definition Z mod B, etc. That, of course, this is not a subspace of that. It's a quotient space of that. And there's an induced map here, pi h. Now, because we're in a Hilbert space setting and we have Hodge theory, this is isomorphic to harmonic forms, which are a subspace. And this is isomorphic to discrete harmonic forms, which are a subspace. So that means I can make this little diagram commute by having some induced map here. But I make no claim, and it's not true, that this induced map is a restriction of this map. It's not true that pi h of a harmonic function is a harmonic function. This is not true. Pi h induces a map from harmonic functions to discrete harmonic functions by this. But it doesn't just simply map the subspace, which would be asking an awful lot of pi h. Okay? So this induced map, this induced isomorphism is not an easy thing to get a handle on. It comes out of this picture. Maybe I should have written the theorem by writing, it's the same theorem that induces a map from here to here from the cohomology groups, and then just reminded you that this cohomology group is isomorphic to this and this is isomorphic to that. So that they have the same dimensions, so there's an isomorphism there also. But then we get this quantitative estimate that said the spaces are also close to each other, but certainly not the same as each other. Okay, and then there's one other estimate that I need for the gap, which is the one in the other direction. So that one's a little bit harder to write. I can't just replace well, let's see. So yeah, so on the left-hand side, I replace the discrete harmonics with true harmonics. And I want this for all Q in the discrete harmonics now. But then what do I put on here? I can't just put I minus pi h of Q, because if Q is a discrete harmonic, that means it's in the subspace, so this would be 0. So the thing that you put here is take the discrete harmonic function Q, project it into the continuous harmonic functions, and the best approximation of that in the subspace, or the pi h of that into the subspace, is the bound for this. Okay, and you see that, I'll just say proof similar, because it's the sort of thing that, if I do it on the board, doesn't make it clearer, but less clear. But again, it's 4 lines. Okay, and these two things easily prove the gap thing, because the gap is just, by definition, the maximum of these two things. And you can read it right off here. So this gives the gap estimates.
Really, you only have to prove the first one of those. Then it's automatic the second follows.
Is that right?
Yeah, at least as long as the harmonic spaces are both finite dimensional.
Okay, I would like to see that, because I don't know that. And actually, I said the proofs are both simple, but one's 2 lines and one's 4 lines. And so if I can get the 4-line one from the 2-line one, I'm happy. Okay, good. The approximation property assumption, when I used that to get the isomorphism on cohomology. So what I proved was that the harmonic part of this coset, I took this coset and I'm trying to prove it's actually 0 coset, so it's only ZB, ZH is 0. So I'm trying to prove this harmonic part of this cycle is 0. I proved that that cycle is orthogonal to its own projection into the subspace, and I used the Pythagorean theorem. And if it's orthogonal to its own projection, then projecting it doesn't get it any smaller. So you don't get that its projection has an error of less than 100%. Okay? So you get Q minus pi HQ is actually equal to Q plus some, you get the opposite inequality there, and that's the contradiction. They use the commutative property of pi h all over the place. So we use the fact that the B part of Z goes to a BH, which is contained in ZH, and so that used all over the time. So actually, that's sort of a nice observation. If you look at these proofs, your hypotheses are a subcomplex with a V-bounded cochain projection with that approximation, and you can point to every point and see where you use exactly those properties. They're all used here.
Can you say something about the assumption?
Which one?
So
that says, okay, we're really assuming this is about one subspace, but we have in our mind a sequence of subspaces such that every element Q is the limit of the pi HQs. So we think for H sufficiently small, that quantity on the left will be as small as we want. So if Q is not 0, that will eventually be satisfied. We're talking about applying it to a finite dimensional space. So it'll be eventually satisfied for the whole finite dimensional space. So that assumption is always met if H is sufficiently small. That assumption says that the space has some approximation power, that it's better to use its projection than to use 0.
the topological property of homologic group shouldn't need that. You don't need this to the holes. I don't know.
So in the examples, I can sometimes get around this and prove it's true for all H, but I don't know how to prove this theorem without that. I'd be surprised. In this weak context, I doubt you can get rid of it.
You do not include that this is the scope of resources homomorphism, but at least these two things should have the same dimension. You don't need that.
They're finite dimensional, so if they're
no, you choose the same number of dimensions. These two homologies.
Well, we can think about it later. I would be very surprised if you could cross out the second sentence and still have a theorem.
No, you don't have a theorem, but I'm saying that you catch the same number of holes.
Well, there's no holes in this. I have an abstract Hilbert complex.
And the dimension of the abstract.
This is an abstract Hilbert complex. For the Durham complex, I might be able to prove something else, but. What's that? If you assume the VH spaces, their union is dense in the whole space, then this property certainly follows for all H sufficiently small. This is the weakest thing I could ever imagine assuming, that there's a small finite dimensional spaces for which the best approximation error is better than 100% error. I mean, this is a minimal, but I want a true theorem, so I make the assumption. But we shouldn't focus on it. Okay, what else can we get if we have a subcomplex with bounded cochain projections? Well, we get the Poincare inequality, which uniform in H, in the sense that the discrete Poincare constant is the product of the true Poincare constant and the norm of the pi h operator as a bounded linear operator from V to V. So this is the discrete Poincare inequality, and the constant I've written explicitly, and it's not the same as the true Poincare, the original Poincare constant at the continuous level, but it's that times the pi h operator. And I think I want to go through this proof also because it really does show how all the assumptions come in. And just to give you a hint, this one is 8 lines, but one of them just says so. So we won't count that. 7 lines. Okay, so we take a V that's in the orthogonal complement of ZH. And of course, when I say that, I mean inside the finite dimensional space. So inside VH, which is what I wrote up there. And we need to prove that Poincare in a constant. The first thing I do is I look at dV. And I say there exists a Z that's in the continuous analog Z perp inside V with the same value of D, such that dZ is dV. By the way, this proof is in both of the papers, the big papers, so you don't really have to copy it down. But so what am I saying here? Well, I take this is something in the range of D. Anything in the range of D is D of something orthogonal to the null space of D. So I can take that thing that's orthogonal to null space of D and has the same image. Okay. Now I use the Poincare inequality at the continuous level, and since Z is orthogonal to the null space of D, the norm of Z is less than the Poincare constant times the norm of dZ. So this is by the continuous Poincare. By the continuous, of course, is in quotes, but the Poincare constant for the original Hilbert complex. Okay, now look at V minus pi h Z. So V is in the subspace, and pi h Z is in the subspace, so this is in the subspace. And let's look at D of pi h Z. Well, D commutes with pi, so this is pi h dz. And dz is the same as dv, so this is pi h dv. But v is in the subspace, and therefore dv is in the subspace because we have a subcomplex, so this is the same as dv. So I used right here commuting and subcomplex property. And I also use the fact that we have a projection. So I use almost everything right there. So we have commuting or cochain map. We have we have a subcomplex, so dv is in the space, and we have a projection operator. So when I apply it to something in space, I get it back again. Okay, so V minus, so d of pi h z is the same as dv. That says d of this thing is equal to 0. So d of v minus pi h z is equal to 0. In other words, v minus pi h z is in ZH, is in the null space of D. Okay, and V was in the orthogonal complement of ZH. So V minus pi HV is orthogonal, minus pi HZ is orthogonal to V. So now we do a sort of, I think Pythagoras again. V in V squared is the same as V pi HZ plus V minus pi HZ. And V is orthogonal to pi HZ, so this term goes away. And that's it. So that's less than the norm of V times the norm of the operator pi h times the norm of z. But the norm of z is bounded by Cp, the norm of dz. And dz is the same as dv. So that's less than Cp, norm of pi, dv times that v. And I cancel out one v on each side, and so I get the norm of v is less than Cp pi h, the norm of dv. So it seems a little tricky, but you just use all the right properties. But what's it basically telling you? It's basically telling you that if you have a computed cochain projection, you can use it to pull down the true Poincare inequality, the one at the top level, to the discrete level. And when you pull it down, you'll bring a factor of the bound of that pi h operator. And so if you can do this where these pi h operators don't have too large bounds, then you're going to have as good as properties on the discrete space as you have on the continuous space. Okay, and now the next theorem has a zero-line proof because we already proved it. We know if you have a Hilbert complex, closed Hilbert complex, and a finite dimensional one's always closed, so if you have a closed Hilbert complex, then the mixed method is well posed, and the inf sup constant depends only on the Poincare constant. The finite dimensional Hilbert complex is a closed Hilbert complex, and its Poincare constant is the Cp times pi h. So therefore, the mixed method is stable. There's a tiny bit, I guess there was a tiny bit to prove here, but what takes no time to prove is the inf sup condition. And the constant of the inf sup condition depends only on the true Poincare constant and pi h. So because of the first theorem, we have that the inf sup condition for the B form, sigma u p tau v q, and now this is in the subspaces, VH cross VH cross HH, and for both of them. This is greater than gamma that depends only on Cp and pi h. That's just applying the continuous theory now that we know what the Poincare constant is. Because the continuous theory said this is greater than or equal to gamma that depend only on Cph, and Cph depends only on those two guys. Let's see here. Maybe I should. this. So what about this next corollary here? Well, let's look at two cases. Suppose there are no harmonic forms on the original continuous sequence. Then there's also no harmonic forms on the discrete sequence because they're isomorphic to each other. We know that HH is, we have an isomorphism between HH and just the harmonic H. So in that case, the last term of this picture vanishes, and actually the p's and the p terms aren't there, and the thing says that sigma minus sigma h plus u minus uh is less than a constant times the best approximation. It says that the Galerkin method is quasi-optimal in the V norm and sigma and u together. Now that's the basic theorem of a stability theorem for Galerkin methods. If you have the im-sup condition, this result holds with a C that's essentially the inverse of that number there. So that we have for free. If we had a conforming finite element method with harmonic forms, then we could also put the P minus PH here and add on here plus best approximation of P minus Q, Q in the discrete harmonic forms. But this is not quite right because the discrete harmonic forms are not contained in the true harmonic forms. So there's one little extra error term. And I think I won't go through it because there's no surprises. You sort of just do the work there. You use a Hodge decomposition at one point. And what you get is one extra term. But let's just look at that term. That extra term is really small because it's the product of two best approximations. So it's basically, in typical applications, the square of the other terms. In typical applications, these first three terms are roughly h to the r or h to the r minus 1, depending on the choice of elements. But this term is roughly h to the 2r. And what is this term? Well, there's a best approximation by things in the whole subspace, not of U, but of the B part of U. So there's that error. So as long as the B part of U is a nice smooth function, that'll be h to the r. And then there's something that's the best approximation of a harmonic form. Well, you soup over the whole finite dimensional space of harmonic forms, normalized by length 1, and you look at the approximation error. This is the quantity we saw before that I argued was always going to be small. It's going to be h to the r. And so the product of those two h to the r things are what comes up. And that comes up exactly by applying the gap theorem, the gap estimates we have. So I don't think I'll go through it again. Okay with that? Okay, so what's coming up now? Okay. And now let me back up, especially for the people who are not super familiar with error estimates for, say, mixed methods. So one example that we could apply this to is we could get error estimates for, say, the Raviart-Thoma mixed method. Of course, that's already been done. We could recreate those error estimates. So when you do that, then you prove something like sigma minus sigma h and h div for the Raviart-Thomas, plus u minus uh and L2, which is the V space for u, is less than a constant times the best approximation, sigma minus tau, u minus V in L2, where u infimum over t in the Raviart-Thomas space, and V in the piecewise constants. So that's in fact, this was proven by Raviart and Thoma, though what they did is prove the im-sup condition, and therefore they had this estimate. For the Raviart-Thoma estimate elements, in the lowest order case, this is piecewise constants plus some special piecewise linears. So it contains P0, but it's contained in P1 on each element. It's not equal to P1. Not equal to either of them. And then the other space is the piecewise constant space. Well, so for the piecewise constant space, this is order H. Now this is a little different. This is the H div norm. So then we have to ask how well the divs of the Ravi-Artomas do. But fortunately, we have, in our context, a commuting projection. So we have div of pi h of tau is pi h of div tau, where this is the projection into Ravi-Artomas, and this is the projection into piecewise constants. This is what Ravi-Artoma used too, way back in '75. And so this is order H also. And so they get an order H estimate for the lowest order Ravi-Artomas in this way. You're not completely happy with it because, for example, how much regularity do you use in this? Well, you use the most regularity when you're estimating the divergence of sigma. To get an order H, you're going to use the divergence of sigma in one higher norm. So you'll use sigma in the 2 norm, which is like u in the 3 norm. So suppose you only care about this quantity. Then you'll get u minus uh is less than a constant times h times u in the 3 norm. You might say, well, that's an awful lot of regularity to get 1 power of h. Wouldn't there be some way that we could estimate this without bringing in all this sigma crap here? And by the way, in that one you can avoid a little bit because you only need the divergence of sigma, which is just f, but there's all sorts of tricks. So then there are other estimates for Ravi-Artoma, which probably reached their pinnacle in the work of Falk and Osborne, and then the work in Douglas and Roberts, where you carefully tore the error estimates apart and looked at each piece and used the Nietzsche trick in duality and saw, well, what could we prove for sigma minus sigma h? And what could we prove for div sigma minus sigma h? And what could we prove for u minus uh? Well, in this case, those are the 3 main quantities. Can we get error estimates for those, both trying to maximize the powers of h's and minimize the regularity of assumptions? And they're more complicated than just the Im-Sup condition. And we did that, and we tried to use every trick that any of these guys ever used for any problem and bring it into the Hilbert complex setting and do it in this degree of generality here and tried to get everything sharp. And I think we got it pared down to close to the minimum, but that's 3 pages. That's not 3 lines, so I'm not going to do it. That's done as carefully as we knew how in the paper in the bulletin. And this is what you get. So I'll take time trying to understand what it says, but I won't go into the proof. So the proof involves the usual Hodge decompositions and Poincare inequalities and the kind of duality arguments that are used to prove in Falk and Osborne and Douglas and Roberts to prove these kind of things. So we already saw this term, which only matters if there are harmonic forms, so you could ignore it the first time through. Best approximation. This is the best approximation of harmonic forms. Putting a pH there restricts it to harmonic forms and sort of normalizes it. So that term's going to, in practice, be order h to the r, or r plus 1, depending on the elements. If the elements contain pr, that would be order h to the r plus 1. Then I need to define 2 other quantities, and these are the sort of quantities that come up when you do duality arguments. What does this mean? I minus pi h k as a linear operator from w to w. Well, first of all, let me convince you that this should be expected to go to 0. What's k? K is the solution to the Laplace operator. That's L inverse. And viewed as an operator from w to w, it's a compact operator, right? The solution of the Poisson equation, or the abstract Hodge-Laplacian. So this is a compact operator. Now, I minus pi h, that's the best approximation in the subspace, that goes pointwise to 0. And you all remember that if you take a compact operator and follow it by an operator that converges to 0 pointwise, you get something that converges to 0 in norm. So this norm is going to go to 0. Okay, what is this? What's the meaning of this? This says, well, take something of order 1, solve the Poisson equation, you get something that's sort of order 1 in H2, although we don't have an H2 here, but that's what you expect. How well can you approximate that back in L2? So that should be an order H squared kind of thing if you have elliptic regularity. So this delta should be order H squared as long as you have linears in your space. If you only have constants in your space, it would be order H. What about the next one? Well, it's the same story, except instead of solving the Poisson equation, you solve the abstract Hodge Laplacian, you solve it and then look at either D or D star of it. So it's like going up to H2, but then applying gradient or divergence or curl and getting down to H1. So that star here means you take the maximum of with a star and without a star. And so this is a best approximation of D of the solution of LU equals F. And so that could be expected to be order H, as long as you have constants in your space. Okay, so we have these three guys of order H, H squared, and H to the R plus 1, something like that. Now, I use the fact that the solution operator was compact. How do I know the solution operator is compact? Well, there is actually an assumption there that we need to make, which is satisfied in all the applications, which is we need to assume that V intersect V star. That's sort of the biggest possible domain that's of the Laplacian. It's a bigger space than the domain of the Laplacian. And we have to assume that V intersect V star is compact inside W. And in all the applications, this is true. And in fact, we use this because this compactness property this implies that the discrete Hodge that the Hilbert complex is Fredholm. And Fredholm implies that it's closed. So this is actually the way that you prove that, say, the de Rham complex is closed. I'll get to that later. But so we make this extra assumption about compactness. And we also make one other assumption. We assume that we have subspaces that satisfy the subcomplex property and have W-bounded cochain projections. Remember, I said that's a little bit stronger than V-bounded. You use that in this argument. With those two extra assumptions, the strength and boundedness of the cochain projections, and the compactness property, and the same old subcomplex property, then here's the error estimates we get. They're a little hard to read, but not too bad. E here means best approximation. So when I write E of tau, I mean the infimum of the W norm of tau minus rho, where rho is in VKH. Okay, and I use that same operator E at all levels, so it just means best approximation by the subspace of that level. Otherwise, there'd be a whole lot of infs on this slide. So the easiest one to bound is D sigma. D sigma H approximates D sigma as well as the best approximation of D sigma. That's it. So that's the best thing you can possibly hope for, that you have the sum of these various pieces. One piece is bounded by only the corresponding piece on the other side. No interaction between the terms. Sigma is a little bit more complicated. The best possible thing would be if sigma minus sigma h was bounded by the best approximation of sigma in the subspace. To that, you have to add the best approximation of D sigma. You say, oh, I don't like that. I lose a power h when I go to D sigma. But fortunately, you pick that power of h back up from the eta term. So you get the right order of accuracy here, although you have a little tiny bit of extra regularity that you're going to need. Well, maybe not, because you're satisfied with one less approximation of sigma. So anyway, you have to look in the specific cases of your space is what you get. But so this should be an optimal order estimate for sigma. Next, you look at du, and you find that du is best approximation of du, plus these two previous things we saw, best approximation of d sigma, which is probably worse, but you get an extra eta in front of it, and also best approximation of p, which should be no trouble at all, and then you even get an extra eta. Then u is the most complicated one. The best u involves the best approximation of u, but also the best approximation of du with an extra pickup of h, also the best approximation of sigma with an extra pickup of h, also the best approximation of d sigma with an extra pickup of h squared, and so forth. So this is what you get if you follow it all the way through. We'll see that when we apply this to the Durand complex and any of the mixed finite elements that we deal with, the PR lambda spaces and the PR minus lambda spaces, turns out that if you have smoothness of the solution, every one of these terms is optimal order. So you get optimal order individually on every term for every choice of elements. And this is probably a good place to stop, isn't it? No, I'll end with the numerical tests. So I did some computations just to show you how this works in practice. These are orange background slides, so this is an example. And I think you'll like this. So I took this problem, grad div minus grad div plus curl rho equals f. This is the 2D thing, so that's the scalar curl of a vector, and then you take the vector curl of it. And I took magnetic boundary conditions. So the Hilbert complex is H1, goes by gradient to H rote. Vector fields goes by rote to L2. The finite element method is the mixed method with spaces V0H and V1H contained in H1 and H rote. These are scalars, these are vectors. And here's the system. And I should have, instead of written D's here, this D and the first two D's are gradients, and the second two D's are rotes. And what elements did we take? Well, the picture I'm going to show you is so-called PR minus spaces, not the lowest order, but the second lowest order, which means we use Lagrange quadratic elements, regular P2 Lagrange elements for sigma, and Ravi-Artoma elements, not the lowest order, but the second lowest order for U. And I need to complete the sequence. This space doesn't enter the method, but I want to complete the sequence for the theory, and I use piecewise constants, which is what's always, piecewise linears, discontinuous, which is what always paired with Ravi-Artomas. Are these kind of pictures familiar to people? Familiar enough? Is there anybody who wants me to take the time to explain them? Say it if you do. Okay, is that, yes, you do? Okay, fair enough. So first of all, you count the number of dots, and that tells you the dimension of the space. This is quadratic polynomials on each space. They have dimension 6. I'm not saying that you could just glance at, and you have to be familiar of these to remember that this is quadratic. But the key point is those quadratics are determined by their values on each vertex and their integral on each edge. Those 6 quantities are the degrees of freedom, which means that they have continuity from triangle to triangle. So this is a space of continuous piecewise quadratics. This is a space of linears, 3-dimensional, but all the degrees of freedom are on the inside, so these are discontinuous piecewise linears, DG elements, discontinuous Galerkin elements. So this is a space of all piecewise linears with no connectivity. This one is a little more complicated. These are vector fields, and the sort of arrows lying along the edge are the tangential components of those vector fields, tau dot s, where s is the tangent vector. So you give the integral and the first moment, or the value at 2 points, your choice. But let's take the integral and the first moment of u dot s on each edge. That's 6 degrees of freedom. And then you also give the integral of each of the 2 components of u in the interior. So those are 8 degrees of freedom. And then you have to be somewhat aware of the Ravi-Artoma space. The second order Ravi-Artoma space is an 8-dimensional space that's gotten by taking P1 vector fields and adding things of the form x comma or y comma minus y comma x times homogeneous polynomial of degree 2, alpha x squared plus beta xy plus gamma y squared. What did I do wrong? Sorry, homogeneous polynomial of degree 1, alpha x plus beta y. So this is a linear part, and this is a quadratic part, but you have only special quadratics. And this has dimension 3 and 3, so this is 6 and an extra 2. And so that's an 8-dimensional space. And Ravi-Artoma showed that for this special space, which we'll understand much better at the end of this course, if you haven't seen it before, this space, those degrees of freedom are unisolvent, and we get a nice space, which is a subspace of H div. So now that's how I'm describing the spaces of piecewise polynomial scalar fields and vector fields by drawing things that indicate what the degrees of freedom are. Okay, so I use quadratics and Ravi-Artomas, which are linears with some extra quadratics added to them, and I solve the mixed problem. This fits into our theory. All the hypotheses are met, so we have the stability, we have those improved error estimates, and now we'll actually look at the rates of the convergence we have. So here I'm only showing the two spaces that we actually use in the computation. And here's sigma in L2, and grad sigma in L2, and U in L2, and rot U in L2. And the rates of convergence couldn't be more crystal clear as being 3, 2, 2, 2. And let's see if that seems right. Well, these are quadratics. Piecewise quadratics in L2 are order h cubed. This is the gradient, so that's piecewise quadratics in H1, so they're order h squared, so these are both optimal. Here we have the Ravi-Artoma space. Those are only linears with only some quadratics, so the best you could do in L2 is h squared. But they have the nice property that when you take their divergence, you get all piecewise linears. That was that DG space, so the divergence or the rotation is also h squared. So everything is optimal, and it clearly works. Now, here the question is, let me go back to this. So we have, for this, my advisor used to say, well, we don't need to do that computation. We proved the theorem. But what if you should really do the computation when you haven't proved the theorem? So what happens if we take a situation where you don't have a subcomplex with bounded cochain projections? Well, there's an easy example of it. I think it's sort of striking, and it's something that I worked on with Rick and Jacob Balakrishnan last year. And I'll just end with that. Suppose we take that same problem. So it's minus grad div plus curl rot. On the unit square again. But instead of the boundary conditions u dot n equals 0 and rot u equals 0 that we did, we just take u dot n equals 0 and u dot s equals 0. Or in other words, we just say the whole vector field u equals 0 on the boundary. Same thing. In other words, this operator is a fancy way to write the vector Laplacian. So all we're doing is solving Laplacian of u is equal to f, where everything's a vector, and u is equal to 0 on the boundary. It's not a hard problem to solve. You could use standard P1 finite elements without mixed methods, and you would have no trouble whatsoever, of course. However, we don't do that. Let's use the mixed method. Okay, so let's write this as sigma is equal to minus div u and grad sigma plus curl rot u is equal to f. And let's approximate sigma by a quadratic, and let's approximate u by a Ravi-Artoma. And of course, put in the appropriate boundary conditions. What does that lead you to? Well, the sigma has no boundary conditions on it, so you have the space H1. But the U has an essential and a natural boundary condition, and the essential boundary condition is U dot S, so it leads you to H0 curl. And here we have the operator grad going out, and here we have the operator rot going out, div going out. And the problem is, this is not a complex. I could put L2. This is not a complex. And why is it not a complex? Because the gradient of an H1 function is not an H0 curl. It doesn't have 0 on the boundary. By changing the boundary conditions, I got a bigger, well, before I had this space, and then this was contained in here, but now I change the boundary conditions, I have that space. Okay, doesn't stop me from computing. I can take this space, I can take this space, I can stick it in the mixed method, and I can compute. But it doesn't have a complex. I can't use all those nice theorems I had. So at this point, there were two possibilities. One is all this fancy theory, okay, it's there, but it's all technical, and really, this method would work fine too. Or two, really all those hypotheses make a difference. You can guess which one I believed in, but we did the computations, and indeed, it doesn't work anymore. It's not a total disaster. It's not a non-convergent method. But if you do this, instead of getting order h cubed here, the computations are showing you're getting order h to the 1.5. And in the gradient of sigma in h1, you're only getting order h to the 1/2 instead of h to the 2. So it's a much worse situation. You're having an error of 0.8 as compared with, in the previous problem, 4 times 10 to the minus 4th. Interestingly, on the U, you actually get the full rate of convergence of h squared. On the rot U, you don't get the full rate of convergence of h squared. You get h to the 1.5. Okay, then there was a little bit of tension between me and Rick and Jay. So Rick and Jay look at this and see, wow, there's a paper. We have to prove all that. And being masters of this stuff and knowing lots of stuff, they saw ways that they could get at it and so forth. And I said, the message is this method sucks. We don't want to tell people about this method. We want to tell people not to use this method. So the result is a paper that was published in M3AS last year, where the introduction says, well, we proved that, so we end up being able to prove all these with some logarithms. And we end up proving all these estimates, but we say the takeaway message is don't use it if it's not a complex. This Hilbert finite element exterior calculus is for when you have a Hilbert complex underlying it. And when you get away from that situation, that's not the right thing to do. These hypotheses are there for a reason. And we also pointed out this is not the only example. Something similar happens if you, in certain situations where you use Stokes problems, and something similar happens in certain examples for plate problems, where if you do things that don't fit so well, you're really doing something like this. And it explains why it doesn't work. Okay. Yeah. A hole in the domain for the.
Well, in your formulation, yours with the harmonic forms, harmonic functions.
So there are no harmonic functions
I know.
for that.
Suppose my problem has a hole in the domain.
No, not all. So suppose I give you a Hodge-Laplace problem with a certain domain. It has certain holes, it has certain voids in it, and it has certain boundary conditions. Here we have magnetic, here we have electric, here we have Dirichlet, and so forth. You look at, and then we look at the Hodge-Laplace on this. That has a certain dimension, a certain kernel, which is the space of harmonic forms. And the dimension of the kernel depends on the topology of this boundary, the topology of this boundary, the topology of the domain, the topology, all those things. If it's all electric or magnetic boundaries, then I can relate it immediately to the number of holes. It's different for electric as magnetic. If it's all Dirichlet, then there are no harmonic forms, no matter how many holes you have in it. Because the Dirichlet problem has a unique solution. It doesn't depend on it, right? We never said that if we want to solve Laplace U equals F, U equals 0 in the boundary, and there's 11 holes in the domain, we have to mod something out. No, it's a perfectly well-posed problem. Whether the discrete one, I don't know. I suspect the discrete one also probably has a unique solution, but it's not a stable approximation, so I don't want to use it. I don't go there.
Let's assume that we have a pure magnetic quantity.
Yeah.
One hole.
Yeah.
You do have one.
Oh, so you're just asking you're going back to the good case. Yeah, okay. So how do we compute, for example, going way back, let's see if we can get back there. Nothing faster than this? Must be something faster than this. Going way back to the first lecture. Okay, this here was computed using mixed finite element methods on this domain. So how did we compute that? So what you do, okay, so how did we compute this problem? We take our finite elements and we compute the stiffness matrix like you always do. The only difference is the stiffness matrix has a one-dimensional kernel because there's a hole in there. So then we used eigenvector solver to find the zero eigenvector, which means what we did is the inverse power method, shifted inverse power method. We just applied that singular matrix plus a tiny epsilon inverse to a random vector, and in 2 iterations that converged because we had a tiny epsilon, 2 iterations that converged to it. Then we knew the coefficients of the harmonic I, and then we put that into our numerical method and said, okay, find something orthogonal to that solves the rest of the equations, and we got this.
In your new mixed finite method, you do introduce the PH or HK, right?
Yes, you have to compute with it.
Three functions. One of them is harmonic functions.
Yes.
So do you do the computation based on the discretization of them?
So as I say, you create the finite element matrix. Its kernel are the discrete harmonic functions, and they enter into your numerical method. Okay, so suppose I have a finite element space, VH, and so I choose a basis, a local basis, so it's like an Rn, and I have my stiffness matrix, which goes from Rn to, it's an n by n matrix. And suppose I know that the dimension of the null space is equal to 1. And what I want to do is I want to find a coefficient vector u in Rn such that u is orthogonal to this null space and AU is equal to F mod the null space. If I had a basis for the null space, that is, if I knew the vector that spans the null space, this is a pretty easy thing to do. I compute the vector that spans the null space, and I do it.
That's not my question. My question is, you do have a mixed finite method,
Yes.
and you have sigma, u, and p.
Yes.
And p is in the harmonic form.
P is in some tiny finite dimensional space.
So when you're using that mixed finite element to compute your sigma, u, and p, what is the approximation space for your HK? You have a triple.
HK is the space. You don't approximate HK. Your mixed finite element is find sigma h in Vk minus 1h. This is like Lagrange. And find UH in VKH. So this is Ravi-Artoma. And find pH in HKH. This is a subspace, a very small dimension of VKH. And you know the span of it. It's just a span of one, if you have one hole, of one vector, which you compute. So you're looking for something in here that satisfies the condition UHQ equals 0 for all Q in here. And that means you just imply this thing is orthogonal to that one vector which you computed. Okay? Yeah. So now you've probably done the same thing in solving a Neumann problem. But the one difference, the Neumann problem, we know the function is just the constants, and it's actually in the finite element space. Here, well, this is in the finite element space too, because we take discrete harmonic forms, but we don't know it. We have to compute it. So it's exactly the same as orthogonality of the constant in the Neumann problem, but you have to compute what the constants are, because they're really the harmonic forms. Okay, any other question? Umberto. So, yes, you have a Hilbert complex. If you put part is magnetic and part, so you simply define Vk is the set of U in H lambda k, that is lambda k and du, you know what it is, such that the trace on part of the boundary of U is equal to 0 and so forth. So you put the essential boundaries on part of the boundary conditions and the others pop out naturally. Then you have a question, what is the dimensional space of harmonic forms? Well, it clearly depends on how you decompose the boundary, because we know if you do all one, you get something different if you do all the other. It depends on the topology of the different pieces of the boundary. There are papers that have this all figured out. I don't know the answers right off hand. So no longer do you need to know only how many holes and how many handles, but also you have to know how many holes and handles and connected components of the electric part of the boundary and the magnetic part of the boundary. By the way, so I had a student who, as a warm-up project, wrote a code to compute these null spaces and use them. And he wrote it in two ways. One is you can say, well, I know how many harmonic forms there are. There's 3, so jump right to the inverse power method, use a variant that finds triple eigenspaces all at once. Or the other, somebody gave me an unbelievably complicated triangulation. I don't know how many holes there are in this thing. You figure it out. And it computes the Betty number, which is a known problem in computational topology. You compute it first, and then you apply it. And so with this problem, since I'm not a master of what happens, I would say let's put it in there, make the matrix, figure out the dimension of its kernel through computational topology, and then figure out the eigenspace. Oh, we are?
Yeah.
Maybe we just continue.